classic case of the flaw of averages involves a statistician who drowns in the river that's on average 3 feet deep. Of course, the boss asked how deep the river was, and you said it varies. And then the boss said, "Give me a number." At that point, you have to say, well, if you need a number, on average, it's 3 feet. And the rest is history. But here's a more subtle form of the flaw of averages that impacts hazard risk. We have town A. On average, one house burns down per year. We have town B. On average, one house burns down per year. So what's the difference? But suppose that in town A, at random, 1 of 100 houses burns down every year, while in town B, at random, every 100 years, all 100 houses burn down at once. Yikes! Don't blame the fire scientists. They've got these elaborate simulations with prevailing winds and fuel loads and mountains and valleys and all that stuff. But of course the decision maker says to them, "Give me a number." And then they say, well, if you need a number, on average, town A equals town B, 1 house fire per year. What we need here are chance-informed decision makers who say, give me the chances. The chances of what? Oh, that all 100 houses burn down in 1 year, or that 50 houses burn down in 1 year, or that 3 houses burn down in 1 year. And the Chances Consortium has figured out how to bottle this simulation like beer and store it in a beer bottle to deliver to the chance-informed decision maker. The Chances Protocol conveys hazards and natural catastrophes through extracted simulations. And that's really not so easy, because from simulation to beer bottle, there's potentially a millionfold compression of the data. Now, we've done this already. So here's the city of Berkeley. And if we look at Berkeley, see, there's a fire, oh, that's a big fire. You see these polygons here? There's a fire. Now, you're looking at the results of a 10,000-year simulation in which only the big fires were kept. So no dumpster fires, no little brush fires. And out of the 10,000 years of these significant fires, there were 106 actual fires, or a 1.06% chance every year of such a fire. Now, the chance-informed decision maker can say, what's the chance that in a given year we exceed a 10,000 acre burn? And that's apparently 0.41%. Well, how about a 30,000 acre burn? And that's a 0.28% chance. So I think we're really entering a new age here in risk modeling. Let's start with the simulation age, which exists now. Chances are calculated by generating random numbers on computers and counting the number of times an event occurs. And this is like, I don't know, 75, 80 years ago this happened. But we've now entered the chance age, in which the chances are embedded in the data. And most importantly, in the chance age, when the boss says, give me a number, you remember the boss, you say, what do you want it to be, boss? Here are your chances.